In these sections, we're going to look at using what we've learned about electron configurations, that is, how electrons are arranged inside atoms, to tell us things about the properties of atoms and also of ions. And so we're going to look at these things. We're going to first look at trends in orbital energies, and that is that the energies of the orbitals we were talking about, like 2s orbitals and 3p orbitals, etc., aren't the same for each element. We're going to look at the trends for that. Then we're going to look at atomic size, ionization energy, and electron affinity. Those are the three main atomic properties that correlate with orbital energies and with the periodic table position. And then we'll look at electron configurations and sizes and explain why ions are the way they are. So we're going to start out with talking about this in a general sense. The periodic properties of elements all depend on the energies and also the size of the atom's outermost orbitals. That is, the outermost orbitals that are filled, outermost occupied orbitals. And the relative energies of those outermost orbitals mainly depend on what would be their size, the size of the orbitals, how big the orbital is, and also what's called the effective nuclear charge, which we'll talk about in a couple of minutes. So the two trends, the first one is that as you go down the periodic table, you go from using, for example, a 1s orbital to a 2s orbital. So hydrogen would use a 1s orbital. That's from there. Lithium would use a 2s orbital. Sodium would use a 3s orbital. And as you go down the periodic table, those orbitals get bigger, and they get to be higher energy. So larger orbitals, these will be higher energy. These will be lower energy. And they'll be bigger as you go down the periodic table. So that's a pretty easy trend. That makes a lot of sense. Going across the periodic table, what we see is that orbital energies decrease. So as we go from sodium over to argon in the third period of the periodic table, what we see is that the orbital, the energies of each orbital, the 1s orbitals decrease as you go across, the 2s orbitals decrease, the 2p orbitals decrease, etc. And this particular chart will be useful for a number of things as we move through this section of the chapter, because it shows both the relative orbital energies as well as the occupancy of the orbitals. And we'll be using that to explain a number of things. The key, though, is that the energies of all of these different subshells are not the same for different elements, and they decrease moving across the periodic table from left to right. So why do they decrease? Why is it that neon, for example, has lower energy orbitals than does lithium? And the reason is something called, or we explain this using something called effective nuclear charge. And here's the idea. If you have, say, a lithium atom, and we're talking about the lithium atom has a 1s orbital that's got 2 electrons in it, and a 2s orbital that has a single electron in it. If you think about that 2s electron, I'm going to draw this kind of diagrammatically. I'm going to put the nucleus here. It's a 3 plus charge nucleus. What that 2s electron sees is it sees a 3 plus charge. It's attracted to that 3 plus charge in the nucleus. The lithium has 3 plus charge because it's element number 3. But it's also repelled by these other electrons that are in the atom. And so we have an attraction to the nucleus. That's Z, is the charge on the nucleus. You also have this repulsion from the other electrons. That's called shielding. That's S. The net effect of the attraction to the nucleus and the repulsion from the other electrons is the effective nuclear charge. And that's equal to the charge on the nucleus that you're attracted to minus the repulsions from the electrons, which for the other electrons in the atom, which you are repelled by. And what happens as you go across the periodic table, as you go from lithium to beryllium to boron to carbon to nitrogen, oxygen, fluorine, and neon, each step along the way, Z goes up by 1 because you're adding one more proton into the nucleus. So lithium has a Z of 3, beryllium has a Z of 4, boron has a Z of 5. It's just the atomic number. But also as you go across the periodic table, the shielding goes up. And we have a plot here of how shielding goes up and how overall charge goes up. The charge on the nucleus goes up 1 for each atomic number. So this is lithium, and this is neon here, atomic number 10. As you go across, the charge on the nucleus goes up by 1. As you go across, there are more electrons in the atom, and so there's more repulsions, so the shielding also goes up. And these color dots here are the shielding. So that's the shielding increasing. That's the charge on the nucleus increasing, and you can see that the charge on the nucleus increases faster than the charge on the shielding. And what that really means is as you go across the periodic table, this goes up more, that goes up less. And therefore, each step along the way, the sum of those two properties, Z star, increases. So as you go left to right in the periodic table, Z star increases. And what that means is that the charge that an electron experiences for neon is greater than the charge that an electron experiences for lithium, because neon has 10 protons in the nucleus and less than 10 protons worth of electron-electron repulsions. Lithium has 3 protons in the nucleus, and it has also less than 3 protons worth of 3 charges worth of electron repulsions. And so as you go across, the added protons in the nucleus outweigh the shielding, and so effective nuclear charge goes up. These two trends, atomic size going up as you go down the periodic table, effective nuclear charge, Z star, increasing as you go to the right in the periodic table, are the two main things that will play a role in properties of the atoms, and therefore also properties of lots of things atoms do, like what kinds of bonds they form. And so the general periodic trends are that the highest occupied orbital for an atom, meaning, so if we had lithium, for example, what we mean by highest occupied orbital is you'd have a 1s orbital that's got 2 electrons in it. You have a 2s orbital that's 1 electron in it. We're talking about the highest orbital that's got electrons in it. Having electrons in it is what we mean by occupied. The lower left of the periodic table has the largest orbitals and those of the highest energy. And by highest energy, what we mean is most loosely held electrons. And the top right in the periodic table has smaller, lower energy orbitals, and so these have the most tightly held electrons. And we'll see that play out in lots of different ways as we walk through our different properties. And it plays out in molecular structure and molecular properties as well as we move through the semester. Okay, so our first thing we're going to talk about is atomic size, just how big atoms are. And first we have to talk about what do we mean by atomic size. And we normally do it by what's called atomic radius. Turns out that, remember, when we looked at electron orbitals for electrons, you get these kind of clouds. And the idea is the electron doesn't really end at a position. It doesn't end here. The electron cloud kind of peters out as you go away. So the atom really doesn't have a defined edge. So you can't really say the atom goes from this spot to that spot, and that's how wide it is. So what we do is we measure, and it turns out that experimentally this is important, we can only really measure from nucleus to nucleus. And so we take, for an element, we take it bonded to itself, and we take that distance there, half the distance from the nucleus to nucleus, and that's the atomic radius. And so the atomic radius is a measured property, most often measured when something is bonded to something else, preferably to another atom of itself, but not always. The general trends are that as you go down the periodic table, things get bigger. These are atomic radii in picometers. Picometer is 10 to the minus 12th meters. It's a thousandth of a nanometer. And as you go to the right in the periodic table, things get smaller. So notice that lithium, say the lithium 7 atom, for example, has 3 protons, 4 neutrons, and 3 electrons. A neon 20 has 10 protons, 10 neutrons, and 10 electrons. So a neon has about 3 times as much matter, about 3 times as many protons, about 3 times as many neutrons, 3 times as many electrons as lithium has. But notice a neon is much smaller than a lithium atom is. And the reason for that is that neon has a much higher effective nuclear charge. So even though there are more electrons in its electron cloud, those electrons are so attracted to those 10 protons, they're pulled in more tightly. So the general trend for atomic size is you got big atoms on the lower left, and you have small atoms on the upper right. The next property is ionization energy. And ionization energy is probably the best measure of how tightly an atom holds onto its electrons. And that's because that's what it measures. It measures taking an atom in the gas phase and yanking an electron out of it. So you make a cation in the gas phase plus a free electron. The energy required to do that is the ionization energy. It is always endothermic. That is, it always requires energy to do that. Nothing gives up an electron without some energy being used for that feat. Here's some trends. First, we're going to look at the first three periods in the periodic table. So we see that the ionization energy, that helium is greater than hydrogen, and that actually has to do with effective nuclear charge. We see a general trend going from lithium to neon across the periodic table, that it goes up. Notice when we go from neon to sodium, it goes back down a great deal, and then from sodium up to argon, it goes up. And notice that the third period going up is somewhat lower than the second period. And also notice that there's these zigzags here. So we're going to explain all of those features. So first of all, going down the periodic table, we see that ionization energy decreases. And that's because of larger, higher energy orbitals. And so if something has a higher energy orbital, it's going to be, if an electron's in a higher energy orbital, say for like potassium, it's in a 4s versus sodium's in a 3s versus lithium's in a 2s versus hydrogen's in a 1s. If the 4s is at higher energy, it takes less energy to get that electron out of the atom. So that's easy enough. As we go to the right, there's a general increase in effective nuclear charge. In effective nuclear charge, and that means that the electrons over to the right are held most tightly. And so the most tightly held electrons are those where the orbitals are lowest energy, and the least tightly held electrons are those in the lower left. So lowest ionization energy is in the lower left, highest ionization is in the upper right. Now let's talk about the breaks in the lines, and we'll do this for, looks like we're going to do it for the third period, but the same reasoning works for the second period. So in general, there's an overall trend, and that's an increase due to increasing effective nuclear charge. So generally orbital energies will decrease, as we see here, as you go left to right in the periodic table, and therefore it takes more energy to get them out. What we also see, though, is that from sodium to magnesium, it increases. That makes sense because the 3s orbital for sodium has to go that far. The 3s orbital for magnesium, so this is sodium here, this is magnesium here. The 3s orbital for magnesium has to go further. It takes more energy to get magnesium out than sodium out because the 3s orbital for magnesium is lower in energy. When we go to aluminum, though, we see this break in the line. And the reason for that is, as we go right in the periodic table, the 3s orbital for aluminum is still lower, so that would require more energy, but the electron now that can be taken out is the 3p electron. Because the 3s orbital was filled, the next electron that's added for aluminum is in the 3p subshell, which is higher in energy, so now that takes less energy, which is why that goes down, why it's easier to take it out. The ionization energy is essentially that distance there. Now when we go from aluminum to silicon to phosphorus, each electron is coming from the same kind of orbital. Those orbitals are getting lower in energy as you go to the right, and so we see this increase in the amount of energy required. Erase a little bit of that. Now notice the second break comes about between phosphorus and sulfur. And the thing that happens there is, although the 3p orbitals are lower in energy for sulfur than in phosphorus, so that's sulfur and that's phosphorus, what happens is for phosphorus, all the electrons are in different orbitals. None of them are paired. When you get to sulfur, one of those electrons or two of those electrons are in a pair of orbitals. And so what's happened here is that we have essentially, let's say, a 3px orbital. And if we're taking the 3px electron out for all of those things, for all these atoms as you're going across, it's alone in that orbital. But when you get to sulfur, all of a sudden there's two electrons in the same orbital that has extra repulsions, which makes it somewhat easier to take out. And then because you're taking out a paired electron, it's somewhat easier. And then when you go from sulfur to chlorine to argon, we still see orbital energies decrease, and we're still taking out electrons from pairs, and so therefore we see the trend, the increasing trend with effective nuclear charge, resume its steady increase. Okay, the last of these kind of electron grabbing, electron moving type properties we're going to look at is electron affinity. And electron affinity is the opposite of ionization energy. It's the energy associated with an atom grabbing an electron and making, is a little hard to see, making an anion in the gas phase. And the energy change for that is electron affinity, and it is exothermic when it happens, because it doesn't always happen. Some atoms have no affinity for grabbing an electron and making an anion. And so our trends for this, I'm going to draw a line across here. This is the 0 point. And so these elements have no electron affinity, meaning in the gas phase, if presented with an electron, no cost to them, the electron won't be added. There'll be the electron is not added to that atom. Other things have a negative electron affinity, and that makes sense because the electron affinity is essentially adding an electron to something. It's becoming more stable. That's why it's added, so electron energy is given off. We see the trends aren't as clear as we had for other things, but generally as you go left to right for a period, the second period here, you get an increase in how much energy is given off, and you get that in 2 times. And we see breaks in the lines again, and those breaks in the lines correspond for the same reasons we had before, whether or not you're going filling up an orbital that is already filled, or whether you're pairing electrons, things of that sort. So that works the same way as we saw for ionization energy. But let's in particular talk about why it's sometimes 0. If we look at the ones that are 0, if we look at, for example, lithium's not 0. And so lithium, this is lithium here. Oh, I'm looking at the wrong ones. Let's say sodium. Sodium's not 0. So these are the ones that are here, the 0. Sodium's not 0. And this is sodium here. This is magnesium. That's aluminum. That is silicon, phosphorus, sulfur, chlorine, and argon. And so what we see is for sodium, we have this electron, an electron can go into there, and that's reasonably advantageous because that orbital is relatively low in energy. So you get some energy by doing that. For magnesium, the 3s orbital is filled, so you can't put another electron there. So if you're going to add another electron there, you have to go way up in this orbital here, and that's just not as advantageous. As you go across the periodic table, you'll see other places where this happens, and so the other main place that happens is argon, where argon, it's n equals 3 shell is filled, and because that n equals 3 shell is filled, you'd have to go all the way up into the 4s orbital, and that's less likely to happen. So when you see filled subshells by adding that extra electron, or when you already have a filled subshell and you have to add up to a higher subshell, that's where you see these numbers of 0. Finally, the last part of this is we're going to talk about is ion formation. Why do ions have the charges they do, and what are the electron configurations of ions, and what are the sizes of ions? So first, a reminder that for monatomic ions, which are the ones we're talking about, the group 1A elements have 1 plus charge ions, group 2A plus elements are plus 2, aluminum is plus 3, and then we have anions, group 7A are 1 minus, group 6A are 2 minus, and when we have ions for anions for group 5A, they're 3 minus. And so that's just a trend you memorized, but now we're going to explain why it happens. And also notice that transition metals have often more than one possible cation charge, and we'll talk about why that is as well. No additional fee. All right, so the general idea is, first we're going to talk about why is it that things on the left side of the periodic table make cations, things on the right side of the periodic table make anions. The reason for that is this decrease in orbital energy as you go from left to right. So Z star increases as you go across the periodic table, which means that things on the left have high energy orbitals. Things on the left have high energy orbitals. When there are electrons in those orbitals, because they're high energy, they're easy to take out. So it's easy to remove electrons from orbitals on the left side because those orbitals are higher up in energy. So it's easier to get the electron out. Things on the right side of the periodic table have low energy orbitals, and so when they have vacancies, like as we see here and here and let's say here, those orbitals have low energy vacancies, so electrons can be added into those. And when you can add electrons into an atom, that's when you make an anion. The other thing we see is that the reason that rare gases don't make ions is that their shells are filled, and any electron that you would add would go into an orbital that's too high in energy to make it valuable for an electron to go into it. But then the orbitals that are filled are too low in energy to make it easy to grab an electron out. So for these elements here, the noble gases, they're very unreactive because their filled orbitals are low in energy, so those electrons are not available for bonding. And its empty orbitals are too high up in energy, so they're not good at accepting electrons. Next, let's talk about the charges that we make. So for sodium, what happens is it's got 8 electrons in the n equals 2 subshell, 2 electrons in the n equals 1 subshell, sorry about that, and 1 electron in its n equals 3 subshell. And so what happens is when you make an Na plus ion, you take away the highest energy electron, so you take that away. So Na makes Na plus, and the reason it doesn't make Na2 plus is you'd have to take away one of these electrons and they're lower in energy. So you get rid of the high energy electron fairly easily, but it's not as easy to take away the low energy electrons. For magnesium, we have this, and so for magnesium, if you make magnesium plus 1, you would take away one of the 3s electrons, and you'd be left with this. And that's fine, and you can do that. It's not that hard to do. But what happens is this electron is still relatively easy to remove, and so that electron is also removed. And so you end up with magnesium 2 plus. You don't make magnesium 3 plus because you'd have to take an electron out of the relatively low energy 2p orbitals. For aluminum, the same thing. You can grab these 3 electrons, but not those electrons, so you make aluminum 3 plus. Same deal happens with anions. If you have fluoride ion, the 2p subshell is low in energy, so you can add electrons into it. So you can add 1 electron because it has 1 vacancy. 1 vacancy at low energy. You don't use this because it's too high in energy. So an electron being added to that just doesn't happen. For oxygen, there are 2 low orbital vacancies, 2 low energy orbital vacancies. And so because of that, you can fit 2 electrons in, and you make an oxygen 2 minus ion, the oxide ion. For chlorine, again, you have a high orbital energy 4s orbital. That's not going to add electrons, so that doesn't happen. But you have one low energy vacancy, and so you can add an electron into that. And so all of the group 7 elements, group 7a elements like chlorine and fluorine, all have in their electron configurations a single vacancy. And so that's why you make, let me go back to here, all of the group 7a elements have a single vacancy in their electron configurations at relatively low energy. Low energy because they're on the right, single vacancy because it's group 7. So you've filled 1, 2, 3, 4, 5 of the 6 slots in the p orbitals. And so you can fill in 1 electron. The reason the 6a elements can make 2 minus orbitals, 2 minus anions, is because they have 2 vacancies at low energy. Finally, the last thing we're going to talk about is, or about ion charge, is transition metals. And one of the most important things is that when transition metals make ions, whoa, get back there, you. When transition metals make ions, what they do first is, when they make cations, if we're going to make iron, say, 2 plus, the electrons that are lost are not the 3d electrons, which are the last ones we put in. They are, in fact, what am I doing? They are, in fact, the 4s electrons. The 4s electrons are the electrons that are lost first when you make iron 2 plus. So that's the electron configuration for iron 2 plus, which would be using the rate of gas notation. Oh, I'm still writing in white, so I can't see it. Using the rate of gas notation, it would be argon, and then it would be 3d6. If you're making iron 3 plus, on the other hand, the third electron you take out is from the relatively low energy d orbitals. So the next electron you would take out would come out of the 3d orbitals, and you take out that paired one because the paired one has the most electron repulsions, and then you would end up with argon 3d5. And so when the two things that are important is you lose those s electrons first. That was these ones here. But the other thing that's important is the reason that transition metals can make different ions with different charges is that both the 4s orbitals and the 3d orbitals are relatively similar in energy. So you can grab, one isn't much higher than the other, so you can generally take electrons out of more than just one of those. Finally, ion sizes is our last subject for this. The general thing first is these are ions for group 1A over here, group 2A here, 3A here, and then we have 5A, 6A, and 7A. And one of the first things you see is anions are big, cations are small. And the reason is that anions have extra electrons. And when you have extra electrons, the electron cloud expands. Cations are small because you have fewer electrons. And when you take electrons away, the electron cloud compresses and gets to be smaller. So that's one thing that's true. The other thing that's true is you go down the periodic table, you still have larger orbitals. So as you move down the periodic table, sizes of ions increase. But left and right, things are different. We can think about this for a special kind of set of ions, which are called isoelectronic species, which means the same electrons, which means the same electron configuration. And so if we look at oxide, fluoride, sodium ion, and magnesium ion, they all have 10 electrons. So they have the very same electron configuration. They're using the same orbitals, they're using the same number of electrons. What's different is the number of protons in the nucleus. Oxygen is atomic number 8, so it has 8 protons in the nucleus. Fluorine is 9, sodium is 11, magnesium is 12. And so what we see is oxide is the biggest of those ions because it has the fewest protons pulling those 10 electrons. Magnesium is the smallest of those ions because it's got 12 protons, the most protons pulling those same 10 electrons. So as the number of protons goes up, the size of the ion goes down because you have the same number of electrons being pulled in by more and more positively charged protons in the nucleus. And that concludes our periodic properties of the elements.